Welcome to Module 01, covering IBM AIX and Power Systems Virtualization Infrastructure. In this deep dive technical session, we will audit bare metal processor topologies, unpack kernel operational boundaries, configure isolated hardware partitions, and query relational configuration databases. To fully comprehend the operational stability of the IBM AIX operating system, we must first master the enterprise-grade bare metal infrastructure that supports it, IBM Power Systems hardware. Power Systems frames are built entirely around the Reduced Instruction Set Computer, or RISC, computing architecture, specifically utilizing high-density IBM Power 9 and Power 10 processors. Unlike consumer-grade x86 infrastructure designed for broad commodity workloads, Power Systems frames are engineered with massive multi-threading capabilities, symmetric multiprocessing layouts, and expansive memory bandwidth channels. These frames are optimized for maximum resilience, enterprise virtualization efficiency, and non-disruptive physical capacity growth. This physical foundation allows financial centers, healthcare grids, and global supply chains to run heavy transactional databases securely without risking infrastructure resource bottlenecks or unplanned physical system outages. IBM Advanced Interactive Executive, commonly known as AIX, is an enterprise-class commercial Unix operating system. It is fully compliant with the Open Group's Unix 03 standards and is designed to leverage hardware-level microarchitecture optimizations. At its core, the AIX kernel maintains a strict operational division between user space, where applications execute, and privileged kernel space, which interfaces directly with system memory, processing elements, and hardware controllers. The AIX kernel architecture excels at managing massive, multi-terabyte memory layouts and dynamically managing computing threads across hundreds of independent processing cores. This specialized operating system design guarantees that structural enterprise applications receive predictable execution windows, extreme data throughput capability, and full architectural isolation from adjacent processing streams running on the same physical frame. The true virtualization capability of IBM Power Systems comes from the PowerVM Hypervisor, a firmware-embedded management layer that sits directly above the physical hardware components. Unlike software-based hypervisors that add resource overhead in user space, PowerVM is integrated directly into the system architecture. PowerVM allows administrators to slice a single physical frame into multiple independent virtual servers, called logical partitions or lpars. Each lpar functions as an isolated virtual system running its own independent instance of AIX. The hypervisor dynamically handles critical resource distributions, including dedicated or shared processing pools, virtual networking paths, and virtual storage mappings. This hardware-level hypervisor containment ensures that if an operating system patch or application failure crashes a single lpar, all adjacent virtual servers on the same physical frame continue executing without experiencing any performance impact. A fundamental differentiator between AIX and other Unix or Linux systems is its centralized configuration repository, known as the Object Data Manager, or ODM. While standard operating systems spread system configurations across hundreds of separate flat text files, AIX uses the ODM to maintain a structured, relational database of all system assets, device parameters, logical volumes, and software products. The ODM consists of specialized object classes that track everything from the status of a virtual fiber channel adapter to custom kernel tuning metrics. System management tools like SMIT, alongside low-level commands, interact with the ODM to ensure that every change made to the system framework is dynamically verified, persistently stored, and immediately updated in the active kernel state, eliminating configuration drift and simplifying automation lifecycles. The architecture begins at the physical foundation with enterprise-grade IBM Power Systems bare metal hardware frames, containing scalable high-density Power 9 or Power 10 RISC processor modules and high-bandwidth system memory arrays. Embedded directly above the physical hardware layer sits the PowerVM Hypervisor firmware. This low-latency virtualization engine intercepts hardware calls and enforces absolute resource isolation across the managed infrastructure fabric. The PowerVM hypervisor slices physical resources into discrete, self-contained logical partitions or lpars. Each lpar functions as an independent virtual machine instance with its own dedicated or shared computing slices. Inside the logical partition container, the native AIX operating system initializes its kernel. The kernel handles core threads, manages multi-terabyte virtual memory spaces, and divides privileges cleanly between user space and kernel space workloads. To maintain persistent system state parameters and handle device configurations dynamically, the AIX kernel relies on the Object Data Manager or ODM. This centralized database interacts with administrators to continuously adjust active execution tables. As a systems administrator establishing your initial baseline audit connection to an unfamiliar server, your very first checkpoint is checking the exact release parameter. We execute the oslevel command with the -s flag to check the explicit operating system version, technology level, service pack, and build release date metrics. This ensures we can verify our precise patch levels against compliance baselines before beginning any production administration. Next, we run the bootinfo utility with the short flag option, -p, to verify our system baseline platform profile. This queries the underlying firmware interface to confirm that the active operating system partition is deployed on an enterprise IBM RISC hardware microarchitecture plane rather than an x86 platform emulation layer. To accurately determine the exact physical hardware footprint supporting our instance, we invoke the standard uname utility passing the M flag. This instructs the AIX kernel to extract the explicit IBM machine architecture model and chassis type numbers directly from the predefined device's registry. Knowing this model profile helps administrators determine the exact processing layout boundaries and maximum resource thresholds available on the bare metal chassis. To review our processing runtime entitlement quotas, we execute the logical partition status utility, lparstat, passing the I flag argument. This triggers a deep query against the Hypervisor microcode matrix, outputting our active processing entitlement values, our shared processor pool configurations, and our strict hypervisor resource scaling caps to verify resource limits. We will now run an advanced query against the centralized Object Data Manager registry to pull our active hardware assets catalog. We run the odmget utility, passing a conditional query flag matching status equals 1 against the customized device's object class, or CuDv. This reads the relational database structures directly to generate an inventory list of every single physical and virtual device that is currently active and recognized by the AIX kernel. Moving down into storage management boundaries, we execute the lspv command to generate an inventory of our attached storage media. This command outputs a clean layout block showing every active physical volume, its unique persistent physical identifier string, and the exact volume group tracking cluster it is assigned to. This gives us clear visibility into our baseline storage paths before modifying file systems. To inspect the structural partitions holding our actual operating system files, we invoke the logical volume group configuration tool, lsvg, passing the -l argument targeting RISC. This command dumps the complete structural file system tracking table, allowing the student to confirm that all core root file systems, such as user, var, and home, are perfectly synced and active across the volume group storage members. Finally, we initialize the text-based system management interface tool, or SMIT. This menu engine provides administrators with a highly organized interface shell to execute system modifications. Every item chosen inside the SMIT character menu dynamically generates the underlying low-level commands and automatically writes the corresponding object updates directly down into the ODM database registry, providing an efficient system management workflow. Let's launch our first assessment block. Please evaluate the structural microarchitecture options displayed on your or RISC architecture paradigm. This custom engineering allows for extreme multi-threaded transaction performance and vertically optimized processor memory channels, completely bypassing consumer commodity x86 CISC design frameworks. The correct answer is B. IBM Power Systems hardware frames are built entirely around the Reduced Instruction Set Computer, or RISC, architecture paradigm. This custom engineering allows for extreme multi-threaded transaction performance and vertically optimized processor memory channels, completely bypassing consumer commodity x86 CISC design frameworks. Review the virtualization management choices to identify the specialized, firmware-level abstraction engine that directly connects the system flash ROM firmware matrix. Because it executes directly at the hardware layer instead of adding a software execution path inside a user space kernel, it delivers near-zero latency infrastructure virtualization without the performance overhead seen in commodity hypervisors like KVM or VMware. The correct answer is C. The native PowerVM hypervisor runs as deeply embedded microcode within the system flash ROM firmware matrix. Because it executes directly at the hardware layer instead of adding a software execution path inside a user space kernel, it delivers near-zero latency infrastructure virtualization without the performance overhead seen in commodity hypervisors like KVM or VMware. Isolate the core configuration subsystem unique to the AIX Unix kernel that functions as a single, relational hundreds of separate plaintext files inside the etc. directory. AIX strictly unifies its device states, software package versions, and volume group definitions inside the Object Data Manager, or ODM, database object classes. The correct answer is B. Unlike traditional Unix or Linux platforms that scatter configurations across hundreds of separate plaintext files inside the etc. directory, AIX strictly unifies its device states, software package versions, and volume group definitions inside the Object Data Manager, or ODM, database object classes. Please evaluate the core system's maintenance commands listed to locate the exact tool and flag combination utilized to fetch and mince out the explicit active build level parameters. This output includes the base system version, technology level, and service pack releases to allow administrators to perform precise patch compliance checking. The correct answer is C. Running the oslevel utility with the short flag configuration option, -s, prints out the explicit active build level parameters. This output includes the base system version, technology level, and service pack releases to allow administrators to perform precise patch compliance checking. Analyze this architectural statement regarding processing footprints to determine if the specified hypervisor design parameter is hardware-integrated microcode embedded straight into the machine infrastructure logic. The statement is false. PowerVM avoids user space performance tax entirely by operating as hardware-integrated microcode embedded straight into the machine infrastructure logic. This allows logical partitions to run with absolute speed and separation across the bare metal chassis. Evaluate the accuracy of the operational description detailing the relationship between terminal-based administrative menu screen directly behind the scenes to run transactional queries, additions, or modifications against target object data manager database. The statement is true. Every single operation executed inside the character menus of SMIT maps directly behind the scenes to run transactional queries, additions, or modifications against target object data manager database registry classes to guarantee runtime consistency.